and lesson 6.4 deals with identities and equations. We're going to be doing 2 lessons today. What you need in front of you for this is your unit circle and your formula sheet. And a lot of what we're doing today deals with solving equations. I am not going to spend a lot of time re-explaining how to get the solutions to the equations. This is something we've been doing. We started it at the end of the previous unit and we keep coming back to it. So for example, everybody, if we end up with some statement in this lesson where we have sine of theta equals -1/2, I'll explain very briefly, but not really much, that you should know the 2 rotation angles are 7π/6 and 11π/6. And that's why I want you to have a unit circle in front of you. So we're going to be solving trigonometric equations using trigonometric identities. Same deal as yesterday's lesson. For each of these examples, there is a set of examples that are similar in your textbook. So we are asked to solve this equation for 0 to 2π. And when you look at this equation, you don't know what to do because there's a sign of 2x. We only ever want a trig ratio of x, or a trig ratio of theta. We do not in this course deal with algebraically solving equations like sine of 2x minus cos theta. So we have to change that sign of 2x, and this lesson is called Identities in Equations because we're going to use the double angle identity for sine of 2x. And it becomes 2 sine x cos x, and then we have minus cos x equals 0. And it's funny, I was having a conversation with a former student last night who's taking math in university, and the comment from her, we were talking about trig equations, she said something like this. Basically the prof says, and now you should know how to solve it, which you should. In this course, you should know how to solve this equation. But this isn't university. I just want to prepare you for the fact that in post-secondary, you're not really given a lot of help in terms of the work. We solve this by factoring. You can factor a cosine x out of both sides, or of both terms, and be left with 2 sine x minus 1. And then, since we have 2 factors being multiplied to give 0, we can write that the one factor equals 0 and the other factor equals 0. So what we have done is gone from a lesson 30.6.4 question to really a lesson 30 I want to say 4.4. I'd have to look up the chapter, but this is back in chapter 4 where we learned how to solve these. So we've turned it from a more complicated question to something easier. Briefly, I'm going to erase this because it's not really relevant to the math we're doing. Briefly, but without a lot of explanation, if you look at your unit circle, remember on your unit circle that cosine is the x-coordinate. If cosine is equal to 0, then the x-coordinate is 0 in this location and this location. When you take a look at the next equation, which is sine of x equals 1/2, and if the x's bother you, then change everything to theta right out of the gate. There's nothing wrong with doing that. I'm not going to do that as often. For that equation, we're looking at sine of the rotation angle being 1/2. Sine is the y-coordinate. The y-coordinate is 1/2 right here, which means that these 2 locations are the other positions, because that's where y is 1/2. So we're dealing with those 4 locations. In the first part of the question, that I've highlighted in yellow, we can say the solutions are x equals pi over 2 and x equals 3 pi over 2. Suppose I should write x equals. For the second equation that I've highlighted in green, you should be able to say x is pi over 6 and 5 pi over 6. And even that, everybody, excuse me, that pi over 6 and 5 pi over 6, that was the very first lesson in our very first trig unit. You knowing that this is 1, 2, 3, 4, 5, 6 pi over 6. This is a very cumulative branch of math in this course. Any questions with the answers to A? All right, let's try B. 2 cos x plus 1 minus sine squared. So the problem here is not that we have double angles or triple angles or anything. The problem is we've got an equation with a mishmash, if that's a phrase, with a mixture of cosines and sines. And the identity sine squared theta plus cos squared theta equals 1 is always your way to translate sine to cosine or cosine to sine. For example, sine squared of x is 1 minus cosine squared of x. And we have a sine squared of x in here. There's a sine squared of x right here. And sine squared of x is the same as 1 minus cos squared of x. Okay, so I'm going to rewrite the equation. It's 2 cosine x plus 1 minus 1 minus cos squared of x, because sine squared of x is 1 minus cos squared of x. I hope you're okay with the fact that over here on the right, I went from an identity that used theta to an identity that used x. And now this is equal to 3. I'm going to simplify this. This is 2 cos x plus cos squared of x. Because I have 1, I'll highlight this part that I'm talking about. I have 1 minus 1. Well, that's 0. And then I'm subtracting negative cos squared, so that gives me plus cos squared of x. Another way to look at that, I suppose I don't want to cause trouble for you based on simple things. Another way to look at that is if you put a 1 in front of the brackets here, it's minus 1 multiplied by what's inside. So you get 2 cos x plus 1 minus 1 plus cos squared of x equals 3. Bottom line is you end up with cosine squared of x plus 2 cos of x minus 3 equals 0. I want you to just roll that equation down in those two steps that you can see. Roll them around in your head. And does anybody have any questions about that so far? All right, so now we've turned it into a beginning of chapter 5 question, but this can be factored. What two numbers multiply to give 3, negative 3, and add to give positive 2? I think that would be factored correctly. When I FOIL that out, I get 3x for my outer and negative 1. I get 3 cos x for my outer. I get negative 1 cos x for my inner, so I'll get 2 cos x. This is correct. Now we've got cosine of x minus 1 equals 0. We have cosine of x plus 3 equals 0. The first equation becomes cos x equals 1. The second becomes cos x equals negative 3. We look at cos x equals negative 3. And it just doesn't make sense. Cosine of an angle cannot be outside of the range of values from negative 1 to 1. So there's no solution here. No roots. And where is cosine of x equal to 1? In this location on the unit circle. Now we have to be careful here. The domain was, I'm going to have to go back, was 0 to 2 pi, and it includes 0 because there's an equals to component, and it includes 2 pi, which means our solutions to this equation would be x equals 0 and 2 pi. Does anybody have any questions with example B? All right, let's take a look at example 2, solve this equation. Well, the problem here is the same as the problem that we had in question 1b. There's too many different types of trig ratios here. There's sines, there's tangents, there's cosines. Now, I suppose we could replace this with 1 minus cos squared, but experience tells us that looking at this is simpler. It's going to lead us to something that's more useful quicker, because tangent of x is sine of x over cosine of x, and we're multiplying by cosine of x. And if we replace tan of x with sine over cos, what happens in this equation is that the cosine cancels with the cosine, and we are left with sine squared of x equals 1/2 sine of x, which, I don't like fractions, so let's multiply both sides of this equation by 2. What I'm doing here is the equivalent of what we were doing with a single term with no equal sign, where we multiply the top and the bottom by a number. What I get then is 2 sine squared of x minus sine of x equals 0. I'm just killing 2 birds with 1 stone. Horrible expression, but I'm doing 2 things at once here. I'm canceling the 2 on the right and then subtracting it over. Way back when, we learned that if you have a quadratic term and a linear term, you solve that quadratic equation by factoring a common factor out. Now we're going to have sine of x equals 0 and 2 sine of x minus 1 equals 0. 2 sine of x minus 1 equals 0 is the same as saying sine of x equals 1/2. Where are the locations? I'm not talking about angles here. I'm just talking about locations. Sine of x is 0. Sine of a rotation angle is 0 when the y coordinate on the unit circle is 0. So in these 2 locations. How come I'm looking at the y coordinate? Because it's sine. Sine of x equals 1/2. For the yellow highlighted equation, sine of x equals 1/2 here and here, because this distance is 1 on the unit circle and half of it is there. So the y coordinate equals 1/2 in those two locations. Those are the locations. What we want to do now is look at the domain for the rotation angles. And it says 0 to 360, and we can include 0. So starting with this point, we can say that x is 0. We get now to this point, we can say it's 30 degrees. I guess we want answers in degrees. We get to this point, it's 150 degrees. We get to this point, it's 180 degrees. We get back to this point and say it's 360, but 360 is not in the domain. Now, before I address something which I should have addressed earlier, does anybody have any questions with that example? This is demonstrating to everybody, I hope, why solving simple trig equations needs to be something that you know how to do. I want to go back and I want to look at question 1a. Nope, don't need to look at 1a. I'll tell you what I'm looking for in a second. 1b, don't need to look at it. Now, over here, do we have, I want everybody to just take a breath here and look at the original equation. This is the original equation. Do we have in that equation any non-permissible values? I don't want to know what they are yet. I just want to know if this equation has angles that we're not allowed to use. Definitely. The reason is that the equation contains tangent. If the equation contains tangent, this is in the equation, then in the equation is sine of x over cos of x. That's in the equation. Now don't go too far with this. Don't say, well, yeah, but the cos of x's cancel. It doesn't matter. In the original equation, there's a pesky little denominator here as part of the equation, which means cosine of x is not allowed to be 0. Where on the unit circle, where is, sorry about that, where is cosine of x equal to 0? It's equal to 0 here and here. So that's okay. Those 4 solutions we got are permissible. But if we got one of the solutions and it landed on that pink dot on the top or the bottom, we would have to throw it out because it's not permissible. And we're going to run into one of those sooner or later. Let's take a look at number 3, solve this identity. I'm going to give you a little task here in about 60 seconds to make a decision. You're going to replace cosine of 2 theta with something by using your identity sheet, your formula sheet, but cosine of 2 theta has 3 different things it can be replaced with. My question is, I want you to figure out which of the 3 we should use. And to aid in the communication here, cos of 2 theta is equal to cos squared minus sine squared. It's equal to 2 cos squared minus 1, and it's equal to 1 minus 2 sine squared. A, B, or C? What's our wisest choice here? Definitely B. And everybody's picking up on this. Chloe, could you type a quick response here to this question? Why B? What's special about B that's going to make our lives easier? While Chloe's typing that out, I'm going to put in 2 cos squared theta minus 1. And everybody, if you're thinking about why B, I could ask this question instead. Why not A and why not C? So Chloe, do you know, can you write it out for us, or is it for you just an intuitive thing, meaning it just makes sense that B would be the best choice? Yeah, and I think that's what a lot of people say, Chloe. Yeah, that's a better way to say it though too. There's no sign. See, if I put in A, I'm going to have an equation that has sines and cosines. If I put in C, I'm going to have an equation that contains sines and cosines. Here, now what I have is 2 cos squared theta, and I can subtract that linear term to the other side. And now I'm dealing with something that we can work with. This is going to factor. Let's see, must be 1 and 1. I think if we play around with this a little bit, I'm going to want some help here. Not because I need it, but I want to keep you guys engaged. Does that look like it's factored right? In other words, if we FOIL it out, does it give us 2 cos squared minus cos minus 1? Yeah, I think so too. So now that leads us to 2 inescapable conclusions. 2 cos plus 1 equals 0, which means cosine of theta equals negative 1 over 2. And cosine of theta minus 1 equals 0, which means cosine of theta equals 1. Cosine is an x-coordinate. X equals negative 1/2 here and here. And cosine equals 1 here. I want to look at the domain now. We want a general solution. One of the things I notice, well, let's write out the general solution. Theta equals 0 plus multiples of 2 pi. Theta equals 2 pi over 3 plus multiples of 2 pi. And theta equals 1, 2, 3, 4 pi over 3 plus multiples of 2 pi, where n is an integer. But one of the things I notice is that these 3 positions are all 120 degrees apart. So what I've written for a solution here, which I'm going to highlight in yellow, is fine. There's nothing wrong with this solution. Okay? But an alternate way to write it is to say theta equals multiples of 2 pi over 3. 1 pi over 3, 2 pi over 3, 3 pi over 3, negative 1, negative 2, negative 3. They're all multiples of 2 pi over 3. Any questions with that example? I think you get the idea. What I'm going to do for example 4, which I hope is the last example, it is simply come up with the equation. Well, we might finish it. Let's see. I'm going to rewrite this as 3 cos x plus 2 equals 5 over, well, 5 multiplied by 1 over cos of x. I'm just replacing secant with 1 over cos. I don't like fractions. I'm not talking about me personally. We don't like fractions in equations or expressions. So if there's a legitimate way to get rid of fractions, then we should do so. And we can do that by multiplying both sides of this equation by cosine of x. When I multiply the cos of x into this binomial, I get 3 cos squared of x plus 2 cos x. And when I multiply this cos of x into this monomial, this whole thing is a monomial because it's 5 times. The cosines cancel, and I'm left with equals 5. So now we move the 5 over. And now I am going to pull a university prof statement. You should know how to solve that, but I will go one step further. Is it factorable? B squared minus 4 times A times C gives me 64. It's factorable. So it would be 3 cos x. I guess, you know what, we are going to have to finish this one. I think if we put the 5 here and the 2 here, that's correct. Is that factored correctly? So in order for you to decide if it's factored correctly, you have to FOIL it out. No, you're right, it's not. I think the 2 has to go, what am I doing here? 5. Oh, 5 and, no, where did I get 5 and 2? 5 and 1. Yes? I don't know where that 2 came from. Slipped out of some compartment in my brain. So that's factored correctly now? Thank you. So we can finish this because it's only going to take 30 more seconds. Cosine of x equals negative 5/3. Not in this universe. You can't have cosine being outside of the range from negative 1 to 1. The other equation is cosine of x equals 1. Well, what's the domain? Oh, general solution. Where is cosine equal to 1? Right here. And right here. And right here. So we're going to say x equals multiples of 2 pi. So what you're doing in this section, everybody, is you are changing the equation given using identities so that it becomes an equation that you knew how to solve already. And I'm going to try to keep us on a tight schedule today because I really want to get through the next lesson, which is just an introduction to Unit 5. So there are some questions for you to practice here on page 320 of your textbook. And I'm going to say that we'll go 15 minutes with this. So at 1:35, we're going to move on. And we're going to try to get the next lesson done within about half hour to 40 minutes, which will leave you another 20 minutes or so to work on more practice today. So remember, if you need help, let me know. Quick feedback for me. Too fast, too slow, just right.